All right, here we go, calculus folks. Optimization day 2. You've tried the warm-up question. It should be familiar because in grade 9 we solved these questions. You have a fixed perimeter, 40 meters. What dimensions should you make the rectangle so that you get the maximum area, right? So we've got 40 meters of fence. What shape do we make the pen to maximize the area? And it turns out to be a square, right? And the way we did it in grade 9 was we just did a table of values. We do some table of values and we just look for the best value and say, since since that's the highest one, it must work. But we never ever quite knew, did we, that maybe there was something in here that was better or something that was in here that was better. We never really knew. And so the idea is, can you use calculus to show the same result? And that's what this stuff is all about. So I'm actually going to use the grass technique to set up our solution here. And this is going to, for this easy one that we know the answer, it's going to set us up for our technique. So what are we given? We're given the perimeter is 40 meters, and the um, the advice that was given at the first of these optimization problems was draw a diagram if you can, right? And we know it's going to be a square, except for we don't know that right now, right? So we know that the length and the width, we want to maximize length times width where this is a constraint. So what's required is the maximum area, right? We want to maximize the area, right? And so in our analysis step, and the analysis step is kind of like this is like our brainstorming planning stage is our analysis step. A for analysis is we might think of some formulas. Well, we've got a couple, right? We've got the perimeter formula. Perimeter is 2 lengths and 2 widths, and we've got the area formula. And notice that if we wanted to find the maximum area, what we'd like to do is and this is still planning. This is nothing formal here. We're just sort of planning here. We want A prime so that we can find the maximum, right? So we can go through our max min algorithm. Now there's a problem, right? The problem is we've got 2 variables. We've got an L and a W. And so what do we take the derivative with respect to? We're used to taking the derivative with respect to x, but there's not even any x. Well, that's the idea, is we need to fiddle with these formulas so we end up with only one, we only have one independent variable here, whether we think of it as x or whatever. Well, what are we going to do? We're going to use this. We're going to use the given, right? So here's some more planning step. We're going to use the perimeter was 40 in order to get another equation so that we can substitute in here and only have one unknown. So for instance, let's solve for L. Well, then I subtract 2W from both sides, divide by 2 in each piece here, and I get L is 20 minus W. And see, then I can put that in over here. Then I have area equals 20 minus W times W. Or then I have a function for the area in terms of the width, right? And now I can think of taking a derivative, right? We can take the derivative of this. And it falls out pretty quickly here. So now in the solution step, once I've got my function, once it's in derivative ready form, then I'll find the minimum or maximum, right? So set the derivative equal to 0, and I get 20 minus 2w equals 0. I get w equals 10, just like I expected. Well, hang on here. In the min-max algorithm, there was endpoints we were supposed to check, right? Well, what would be the endpoints? Endpoints. Well, they weren't stated, but look here. If I think of the problem, what are some things that would be natural natural endpoints. Well, it wouldn't make sense for me to have a width that's negative. So note, I'm going to say the width has to be greater than or equal to 0. If it's equal to 0, I'm not going to have much of a rectangle. Similarly, what's the most W could be? Well, some people would say 40. If I use all 40 of the fence along one side, well, that would be the most W. Well, but there's two of them, right? There's a W here and a W there. So what's the most W could be? The W could be 20, right? And in fact, if W was 20, that's when I see the length would be 0. So I'm going to say the width has to be greater than 0, but the width has to be less than or equal to 20 as well. And so that is the natural endpoints of my situation, of my question. And then I'm looking at the area, and this is 100, this is 0, and this is 0. So I get the maximum when the width is 10, and two minimums when the width is 0 or 20. So just like we said, just like we expected, and we've proven it using calculus, the end S, this S was for solution, remember, and this is for statement. The maximum area occurs when width is 10, and then that means the length is 10 as well, right? Because we had this little expression there, when the width is 10, then the length is 10. I can calculate that. And the area is 100, just like we knew. Okay, these are going to get much, much more interesting very soon here. So let's get into, from the warm-up, we'll go into the lesson. And there are a bunch of classic question types here. So these ones are measurement and distance. We've already done one of the measurement ones. And so solve optimization problems drawn from a variety of applications, including real life. This is the farmer and the fence problem. So Ferd, this is farmer Ferd, I suppose, has 200 meters of fence to build a rectangular enclosure for his tapir and tamarin. And as everyone knows, you cannot keep tapir and tamarin in the same pen. See, aren't they cute? There's the tapir and there's the tamarin, and apparently they don't get along. So we have to have them in two separate pens. One side is next to a stream as shown. How should Ferd build the pens to maximize his area? He's got 200 meters of fence. How does he set it up so the area is maximized? And the two, does it say the two pens are equal area? Well, we're going to assume that the two pens are equal area. So how do we set this up? Well, the first part, the given, is we try a diagram. And this one's already drawn for us, but we're going to start labeling stuff here. We'll start thinking about this. So we have, what else are we given? We're given 200 meters of fence, right? Great. And what are we required to do? We're required to maximize the area, just like in the first one. Right? All right, well, in our planning stages then, here's our analysis. Then, well, what are we given? Well, notice it's not really a clear perimeter question. We've got bits and pieces all over the place. And you might be said, well, let's call this the width. Then there's the width, and then there's the width. And I could call this entire thing the length, but then I'm going to end up dealing with fractions, right? Because one of the areas would just be this times this, right? So I'm going to let this be L and this be L. Because then what do I have? I have the perimeter is 3 W's, right? Here, here, and here. I don't have to worry about fencing in along the stream, plus 2L, right? But I know that that is also 200 meters of fence, and that's 3W plus 2L. And what's the other formula? Well, I'm interested with the area. I want to maximize this area. So what's the maximum area of this whole thing? The area is the length, which is actually 2L, isn't it? Times the width, which is 1W. All right, dandy. Now, there's a number of ways we could do this, because we've got to fiddle with this formula until we only have one independent variable. So here's my constraint, and I can solve for it. How's this going to work? I'm going to go like this. I'm going to solve for um, L. Notice that if I solve for W, looking ahead, dividing by 3, it doesn't go. So I'd end up with fractions. I don't want to do that. I'm going to divide by 2 on both sides, and then everything should go reasonably nicely. So this is 100 minus 1.5W equals L, and then I could substitute back into here, and then I'm going to have 2 times that expression. I'm going to have to make that bigger. I'm not going to squish that expression in there, am I? All right. And then times W. That is L. So if I take out the L, I'm going to fill it in with what L is equal to. And then now there's my analysis step. This is going to be the function that I want to maximize. All right, well, what do I got? Here's the solution. And notice that all of this planning is important, right? All this planning is important. But where does the real calculus happen? I suppose you could say it happens here. And I'm going to, what was that? That was a W there. So I multiply through, what do I got? I got 200W and then minus 3W squared. Does that make sense? 2 times 100 is 200 times W is 200W. And then 2 times 1.5 is negative 3 times. Yeah, yep, good. There's my formula. And now I'm ready to go through my min-max. Well, before we do that, let's set up our endpoints. Let's think about the endpoints. And I'll do that part of my planning stage here. So certainly I could have W be 0, right? And that's not going to be a very good pen again. So 0 is going to be less than W. And why am I picking W to pick on? It's because that's what I chose as my independent variable down here. All right, well, what's the biggest that W could be? Well, notice I could have length be 0. If the length is 0, then I'm going to use my 200 meters for each of these W's, and it's going to be 200 divided by 3, right? All 200 meters divided by the 3 widths, and those are my endpoints. And notice that those are going to be the ones that give me the area. The area is going to be 0 here, right? And the area is going to be 0 here, and my maximum is going to be somewhere in between those two. So I got to take the derivative. And then set the derivative equal to 0. And then solve. And again, this one's not very hard to solve. I get W equals 200 divided by 6, or what's that? That's 100 divided by 3. Okay, dandy. So then what do? In my solution, I've still got to check my endpoint. So I've got W, here's the one I think it is going to be, probably. Then I got 0 and 200 divided by 3. These both give me an area that are 0 and 0. And now I got to put this in this fraction, this awful fraction, into my area formula to calculate it. So area of 100 over 3, I'm going to go 200 times 100 over 3 minus 3 times, I'm squishing, 100 over 3 squared, calculator, and I get, I think, 10,000, check that on your calculator, over 3. 10,000 over 3 meters squared. So then minimum, maximum. There's your maximum. We were asked to maximize the area. The maximum area. And what were we actually asked to, how should Ferd build the pens? The maximum area occurs if the width, and that's away from the river, so W, away from the river, this thing, is 100 over 3 meters. And the length, and we'd say parallel to the river, is, well, whatever L is there. L is 1.5 times W. Um, that turns out to be 50 meters in total. There and there, 50 and 50. That's it. That's the maximum area. That's how Ferd should build the pens. Dandy. Okay, so in part two, we're going to pick up with some other measurement and distance questions.